Hello and welcome to this next lecture on pattern recognition. As you know, we have been discussing the multi-layer feed-forward neural networks. We looked at them in general, and last class we looked specifically at multi-layer feed-forward neural networks as good models for representing nonlinear functions, right. So, as I said last class, our interest in multi-layer feed-forward neural networks is that they provide a good parameterized class of nonlinear function. We have seen that last time, and basically the way the network represents a function is through composition of linear sum and sigmoids. So, essentially each node calculates a weighted sum of its inputs and passes it through a nonlinear activation function to compute its output. So, we do it for all nodes in a layer and from layer to layer. So, if we do it successively for each layer, we essentially transform the inputs at the layer 1 to the outputs at the final layer, right. So, the actual function that is computed by this is very much dependent on the interconnection weights, because given a particular structure, the only thing that can change is the interconnection weights. So, by changing the interconnection weights, we change the function that is being represented by the network. So, roughly an architecture represents a class of functions and specific weights represent a specific function. So, we would essentially choose the weights to be able to represent a specific function of interest. So, we actually discussed an algorithm for training the network. So, like all other classification regression models that we are considering, the training proceeds by having some training samples. So, we are given examples xi, yi, yi is the target, xi is the feature vector or input vector, and we need a function relationship such that given new x's I can predict the y's properly. So, given the training examples xi, yi, we have to learn the model. So, in this case we have to learn the weights. So, we actually discussed last class an algorithm that is used for training the network. What do? We actually learn the weights by minimizing the empirical risk and the square error loss function. Once we fix the architecture of a network, as I said earlier, it represents a class of functions. So, we can think of that as the class of functions, a class of classifiers H that we are currently considering in the risk minimization framework. Then we have chosen the square error loss function. So, the loss is square of the difference between the output of the network and the desired output. So, we choose the empirical risk of this, that is sum the square error over all the examples and minimize that over the weights. So, we want to find weights to minimize the empirical risk and the square error loss function, and to do the minimization we have chosen the gradient descent method of minimization. Essentially, given the current weights, we find the next weights by from the current weights going down a little bit along the direction of the negative gradient. Okay. That is the standard gradient descent method of optimization, and for this class of networks you derived a very interesting recursive formula for calculating the partial derivative. Essentially, when you are doing gradient descent, a new value for a weight wij is the whole value of the weight minus some step size into the gradient of the performance index with respect to that weight. Now, we showed that all these partial derivatives, the gradient components, can be calculated in an interesting recursive manner, and we derived this recursive formula last class. Okay. So, that is what we are going to start discussing today. So, let us first summarize the method of learning weights. Okay. So, what is that we want to do? We want to learn the weights wijl. Recall that wijl is the weight that connects node I in layer L to node j in layer L plus 1. We are using layered feed-forward networks where interconnections always connect nodes in one layer to the nodes in the next layer. So, nodes in layer L can only connect to nodes in layer L plus 1. So, that is why we have a notation whereby wijl is the weight that connects node I in layer L to node j in layer L plus 1. Now, this we want to learn the weights for all such I, j and L, that is the whole set of weights we represent by the matrix W. Now, we want to learn this W to minimize the performance index J, where J is defined as J of W is summation S equal 1 to n J S W, where S is an index that goes over the training samples. Our training samples are the form XS ds. For the input XS, the desired output is ds. Okay. There are n training samples. So, sum over each of the training samples. So, JSW is the performance measure error on a single training sample, and that is given as capital L is the output layer. So, J is the node index in the output layer. So, YJL is the jth output of the network, which of course is a function of the input XS and the weights W. So, this is on the input XS with the current weights W, this is what my jth output says, because ds is the desired output, dsj is the jth component of the desired output. So, I square this and sum over j, that gives me the error, the square of the error between the output of the network and the desired output, because the desired output itself could be a vector, as a matter of fact, assume it to be a vector of as many components as there are nodes in the output layer. So, YJL is the jth component of the network output, DSJ is the jth component of the desired output. So, this gives me the square of the error, sum over j, that gives me the square of the error between the vector network output and the vector desired output for the input XS. I sum it over all SS, that gives me the, so to say, something that is proportional to the empirical risk under the square error loss function over the training samples XS and DS. Okay. So, essentially we want to find W to minimize J, minimize the squared error, and the way we are minimizing is we are using iterative gradient descent. What will be the iterative gradient descent? Wijlt plus 1, T is the iteration count now, Wijlt plus 1 is Wijlt minus lambda times derivative of Jw, partial derivative of Jw with respect to Wijl, because Jw is sum of JSWs, the derivative will also be sum of these derivatives. So, I get Wijlt plus 1 is Wijlt minus lambda is the step size for gradient descent times S is equal to 1 to n, the partial derivative of each of the JSs with respect to Wijl, right. If you look at it, each JS is actually the same structure. The only thing that different is it is the square of the error between the network output and the desired output, but in the S term I put XS as the input to the network and then find the desired output and use the Sth desired output. Okay. So, when I find the network output, I put XS as the input and then find its difference with the Sth desired output. Except for this, each of the JSs are same, just that I put different XS at the input and use the different desired outputs. So, essentially each of these partial derivatives would have the same structure, but this will be my gradient descent minimization. For each I, j and L, Wijlt plus 1 is Wijlt minus lambda times derivative of capital J with respect to Wijl, which is sum S is equal to 1 to n, partial derivative of Js with respect to Wijl. So, essentially for each training sample XS ds, we will compute the partial derivative of Js with respect to Wijl. Once we do this, we can calculate the this sum and hence implement the gradient descent, right. Then we can update all the weights. Now, this is what we call a batch mode operation. In the batch mode operation, you first put x1, right, and you get the output of the network, then you know the D1, using that you find del J1 by del Wijl, then you put x2, using that you can find the output network for in response to x2, then you find the error with respect to D2, the desired output for x2, then once again find the second partial derivative and so on. You put all the partial derivatives and sum them up and then use that sum to change the weight, that is the batch mode operation. In analogy with LMS, we can also have a incremental mode operation, whereby at each iteration I will only use one of the training samples, then essentially this summation will not be there. Whichever is the training sample I am using in the current iteration, I find gradient only with respect to that training sample. There is not much difference between the two things, because essentially except which XS I will put in the input and which DS I use for finding the outputs, the JS structures are same, and hence the partial derivative computation will also have similar computations. Okay. Now, we have shown last class that for these networks there is a very nice structure for the partial derivatives. The partial derivative I want is del Js by del Wijl. Okay. I did not put the S here because all the JSs have the same structure. So, let us for now forget about the index that tells me which particular training sample I am looking at. Then I can roughly write it as del dou j by dou njl plus 1, dou njl plus 1 by dou Wijl, because the only way a weight Wijl will affect the j is by affecting the output of the network. The only way it can output the affect the output of the network is by its effect on the net input into the jth node layer L plus 1. Wijl is a weight that is connecting into the jth node in layer L plus 1. So, it can affect the total input only into the jth node in layer L plus 1. So, the only way Wijl can have any effect on your final error is by its effect through the njl plus 1. So, the partial chain rule of partial differentiation tells me that this derivative can also be written like this. Now, we said that we can write this as dou j L plus 1, and this one we know because njl plus 1 is a linear combination of all the inputs from layer L, and if I take the differentiation with respect to one of the weights, I get that corresponding output from the layer L. Okay. And this first term, which we called delta j L plus 1 is called the error at that node, and is defined by, in general, delta j L is the derivative of the error with respect to njl, total input to node j layer L, because here I want node j layer L plus 1, this becomes delta j L plus 1. The delta j L's are called errors at a node. We will just remember that the delta j L actually depends on the particular training sample, right, because here just to keep noting simple I dropped that S, but the delta j L is derivative of the square of the error with respect to the net input into that node, but this depends on which particular training sample I am talking about, because XS is, if I am talking about this training sample, that XS will be the input to the network and the final output's error is calculated with respect to that DS. So, delta JL of course depends on the training sample XS DS, but our notation does not explicitly show it, it only gives delta as only the node number as its subscript or superscript. So, even though we do not show it, we mentally remember that dependency is there. So, coming back, if I want to implement the gradient descent, this is the only partial derivatives I want, and these partial derivatives are given by this. So, if I know the error at each node, I can implement the partial derivative. So, now this of course, I know this is the output of a node. So, I just need to know how to calculate delta JL. Okay. We have seen that delta JL can be computed through an interesting recursive formula. Right. Let me first put down the recursive formula. We showed that for the final layer, delta JL is simply YJL minus DJ into F prime and JL. YJL is the jth the output of the jth node in the final layer, DJ is the corresponding desired output. This is the actual error into F prime and JL. This happens to be delta JL by explicitly calculating that partial derivative. And for all other layers, the delta JL satisfies a very interesting recursive formula like this. Delta JL can be given in terms of delta S L plus 1. If I know delta S L plus 1 for all S, then I can calculate delta JL for every J. So, if I know the errors for nodes all the nodes in layer L plus 1, then I can calculate errors for all the nodes in layer L. So, because I know at the output layer capital L, I can calculate at capital L minus 1, then I can calculate at capital L minus 2 and so on. So, using this recursion, we can calculate the errors at all nodes. So, this is how the recursive formula is derived, this particular recursive formula. Recall that delta J L by definition is dou j by dou n j L. So, how does net input into node j layer L affects the final output? Node j layer L its net input is converted into its output and its output is sent to all the nodes in layer L plus 1. So, sum over all nodes in layer L plus 1 dou j by dou net input of node S in layer L plus 1 into dou eta n L plus 1 by n j L, and this can further be written in terms of the outputs. So, n s L plus 1 by del y j L and del y j L by del n j L. The nice thing is this already has a name, that is delta S L plus 1, and because the net input into any node in layer L plus 1 is a linear combination of the outputs of layer L, I get that weight here, and an output of a node to its net input is connected by the activation function. So, this partial derivative gives me the derivative of the activation function. So, this is how we actually derived the previous recursive formula, that is our recursive formula. Okay. So, now we are almost done. So, we know that this is what we want to implement. This is my gradient descent that needs me to calculate these partial derivatives, and I know how to calculate these partial derivatives, that in terms of error at that node into the output. So, if I am asking how to update weight that connects node I layer L to node j layer L plus 1, then the output of node I layer L multiplied by the error at node j L plus 1, right. So, this W I j L connects node I layer L to node j layer L plus 1. So, I take at the input end of that arrow the output, at the output end of that arrow the error. So, I multiply the error at node j L plus 1 with input at node I L, and that product gives me the required partial derivatives. When the partial derivatives are there, of course, I can implement the gradient descent and hence my learning algorithm and the partial derivatives themselves are obtained through an interesting recursive formula. This is the formula for the output layer, and for all other layers this is the recursive formula. So, now what we are going to do is to look at what this particular recursive formula means. So, coming back once again, this is the output, this is the error for all nodes in the output layer. This is exactly like the usual error for a LMS algorithm, right. YJL is the actual output of the network, the jth component, DJL is the desired output, jth component. So, take that, that is the actual error, okay. Multiply by f prime, because f is the function that connects the net input into that node to its output. So, that is the. So, for example, if I have only one node in the output and still I use the sigmoid activation function, but I have no hidden nodes, then this is what would have been the LMS algorithm. Okay. Now, it is very similar to LMS algorithm for a single layer, a 2-layer network. So, this is understandable. Now, let us consider, because we have a recursive formula, once we know all the errors at layer L, we can calculate errors of nodes in layer L minus 1. So, let us look at that recursive formula. If I want error at node j layer L minus 1, then it is some linear combination of errors of nodes in layer L, right. Ultimately, of course, multiplied by f prime of this particular node. So, that does not come with summation, that will keep separately. So, if I want error at node j in layer L minus 1, we calculate it as a weighted sum of errors of nodes in layer L and multiply by f prime, right. That is how we get errors for nodes in layer L minus 1. And in the linear combination or weighted sum, the weights are same as the weights that connect the corresponding nodes in layer L minus 1 to the nodes in layer L. So, essentially I am taking the errors at nodes in layer L, multiplying them by weights. The weights are the same weights between layer L minus 1 and layer L, and take a summation. Right? Let us look at it from the network. So, this is the layer L. Let us say I want to calculate, this is layer L minus 1. Let us say I want to calculate error at node j layer L minus 1, right, that is delta j L minus 1. How do I calculate? For that I have to do delta j L into W j s L minus 1. Delta j L I expanded here, right. We know delta j L is given by this. So, I just expanded that. So, this entire thing is the errors for nodes in layer L multiplied by W j s L minus 1. What is W j s L minus 1? That connects node j in layer L minus 1 to node s in layer L. So, we can think of it as if this is my network. Normally, when I am doing my output calculation, I take the output of node j, multiply by this weight and goes to this node, or multiply this weight and it goes to this node and so on. Instead of that, now we can think of this as, I think that this is the error at this node, not think this is the error at this node y 1 L minus d 1 into f 1 prime, at this node is y s L minus d s into f s prime. We think of that as the current values of these nodes, multiply the current values of these nodes with the corresponding weights, right, and sum it up over all these nodes. That is what I am doing. I am taking delta S L, that is the error at this node, delta S capital L, and multiply it by with this weight W j s L minus 1 and sum it over all nodes in the layer L. That is this term, the term in this big parenthesis, and then multiply by f prime of net input of this node, that gives me the error at this node. Right. Now, this particular style of computation is same at all levels. What do I do for remaining layers? Same thing, delta j L is written as a linear combination of errors of nodes in layer L plus 1. Right. Once again, if is little L plus 1 is this layer. So, I take error at this node, that is delta 1 L plus 1, multiply with W j 1 L with this weight, then I will take delta S L plus 1 multiply delta j s L and so on, add all of them up, that gives me this term, and multiply by f prime of this node. So, essentially if I calculate weights at each of these points, then I multiply these weights, the errors at the node with the weights. Earlier what am I doing? When I am doing forward computation, I calculate output here, output here, output here, then take the output here, multiply by this weight, take the output here, multiply by this weight, take the output here, multiply this weight, that gives me the net input into this node. Instead of that, for actually getting errors at each of the nodes, I have to take the error at this node, multiply by this weight, error at this node, multiply by this weight, error at this node, multiply by this weight, add them up. Right. So, it's structurally the same computation as earlier. So, we can think of the forward computational output as forward propagation of inputs into outputs. I can think of this as the backward propagation of errors. So, that is why this particular way of calculating all the partial derivatives using errors at nodes is called the backpropagation algorithm. What it does is, it does backpropagation of the errors. Once I know the errors at the output layer, I backpropagate, so that I get errors at layer L minus 1. Then I backpropagate, I get layers at L. This is what backpropagation is all about. Okay. So, now let us fully understand what is involved in training the network. Okay. So, we have to do the same process for each training example. So, let us look at it any one example. So, let us say XS DS be an arbitrary example. XS is has got n1 components, because n1 is the number of nodes in first layer at the input layer according to our notation. and D will have n L components, n capital L components, once again notation, that is the desired output. Okay. So, essentially learning a function from n1 dimensional space to nl dimensional space. So, what do? We first have to calculate the output of the network YL, okay, which will have nl components. YL we have to calculate when the inputs are x's. So, I will put x's at the inputs and successively calculate the outputs. Okay. Right. So, this is what we do first do, and we can think of this as the forward computation. Okay. So, what do we have to do for forward computation? We first put the current input x's at the input layer, and then successively from layer 1 onwards keep calculating outputs at the next layer, right, and then at the end we will have the output of the network. Once we calculate the output of the network, then we know the desired output, and hence we can calculate delta J capital L for each node in the output layer, right. Once we calculate that, we can calculate for layer L minus 1 by back propagation. This is the backward computation. So, starting with layer L minus 1, I can keep back propagating errors and keep calculating errors at each of the nodes backwards. I will first calculate errors at node L, then I calculate errors at node L minus 1, then I calculate at L minus 2 and so on. So, this is the backward computation. At end of the backward computation, all the errors delta JL are known. Now, we can compute all the partial derivatives and update the weights, right. Now, let us go into the details. For the forward computation, computing output network, how do you do? Layer by layer. For the input layer, yi1 is xis. yi1 is in the one superscript is for the input layer, I the ith node. So, the ith node simply takes the ith input xis. For all other layers, layer 2 onwards, I first compute the net input eta jl as the weighted sum of the outputs from the previous layer, yi l minus 1, wij l minus 1 summed over I, okay, and then I pass it through an activation function. This is the forward computation, right. So, essentially for the forward computation, for every weight in the network, different weights are in different layers, but for every weight in the network, I have to do one multiplication, and for every node in the network, I have to do one function computation. So, this is my forward computation. Once we have we do it for all the way up to layer L, we have the output of the network, and now we can start calculating the errors. At the output layer, once I have yjl and this is from the training input, the desired input, I can calculate the errors for all nodes in the output layer. Once I have that, I start going back from layer L minus 1, L minus 2 all the way up to layer 2 to compute delta JL. Right. Once I compute all the delta JLs, I can update the weights. Of course, I have written it as a incremental version here, of course, otherwise we have to do it, put a summation here, but this is the overall view. So, we have a forward computation. That is my forward computation. First I get the output of layer 1 nodes, which are simply the inputs, and then from layer 2 all the way up to L, I calculate net input and pass it through an activation successively. So, first I do it for layer 2, then I get all the outputs of layer 2. Now, I can calculate net inputs into layer 3 and so on. Right. Ultimately, I will get outputs of layer L, which is the network output, and then I have the I will calculate all errors, first errors at the output layer, and then using my recursive backpropagation formula, I calculate errors at all the other nodes going back in the layers, and once all the deltas available, I can update the weights. Okay. So, this is the backpropagation algorithm for training the network. So, let us sum it up. We train the neural network by minimization of empirical risk under the squared error loss function. We are given some, we are essentially looking at training the neural network to represent a function. We are given xs ds, xs belongs to some n1 dimensional space and ds belongs to some nl dimensional space. I am learning a function from Rn1 to Rnl. Right. So, we train the network by minimizing the empirical risk under squared error loss. For minimizing the empirical risk, which is essentially sum of squared errors, which much like your least squares method, we use the gradient descent for the minimization. Right. Because of the network structure, the needed partial derivatives are computed very efficiently, right. What is the process involved? One forward pass to compute outputs of the network and one backward pass to compute all the errors and hence all the derivatives. So, first there is a forward way of pushing inputs of the network to the outputs of the network, which involves of course weighted sums and function computations. And once I have the output of the network, by comparing desired output I can calculate errors at the output node. Now, I do back propagation, which once again simply involves weighted sums and function computations. So, one forward pass to compute the output of the network and one backward pass to compute all the errors and hence all the needed derivatives, okay. And then I can update the weights and keep going on. This iterative algorithm for learning weights in neural network is called the backpropagation algorithm. It is short for backpropagation of error. As a matter of fact, backpropagation algorithm has been historically so successful in neural networks. For a large majority of neural network model users, use of feedforward neural network models is synonymous with backpropagation. This course, as I said, we are using backpropagation for training feedforward neural networks. It is a very good algorithm for feedforward neural networks, but we will see that there are other methods of training neural networks. But in spite of that, for feedforward neural networks where we have this kind of sigmoidal activation functions, backpropagation is the most famous algorithm for training the network. Okay. Now, let us look at a few issues about backpropagation. Suppose we have MW number of weights, total number of weights in the network between all layers, counting weights between all layers. Let us say MW number of weights in the network and there are ML number of nodes in the network. Now, the forward computation, what do I have to do? I have to do weighted sum. In the weighted sum, each weight is used only once exactly. So, I will do in calculating the net inputs of all nodes in the network put together through all the layers, I would do as many multiplications as there are weights. So, MW number of multiplications I have to do. We can assume that each function computation is some constant times a multiplication cost wise. I do as many function computations as there are nodes ML. So, totally my computation is MW multiplications plus some constant times ML multiplications, right, or ML function evaluations. So, we do one multiplication per weight, one function evaluation per node. So, the total computational complexities should have been MW plus ML, MW multiplications plus K times ML. So, it is an order notation, so K does not matter, but often MW is the order of ML square, because a weight connects every pair of nodes. So, if I have got 10 input nodes and 10 output 10 hidden layer nodes, right, there are 20 nodes, but I will have 400, I have 100 weights, because each of the 10 input nodes are to be connected to each of the 10 hidden nodes, right. So, normally the number of weights is of the order of square of the number of nodes. So, MW plus ML is the same order as MW, because MW grows as ML square. So, the forward computations complexity is essentially order MW. I will do of the same order of multiplications as the number of weights in the network, and very reasonable, because to compute outputs each weight participates in a weighted sum computation once. So, total number of multiplications is of the order of the number of weights. Of course, of the number of weights plus number of nodes, but we left out number of nodes, because number of weights is an order higher than number of nodes. What about the backpropagation? Backpropagation, the nature of computation is same. Essentially, you think of the errors at the output nodes like the inputs at the input layer, and then do the same kind of weighted sum calculation. So, for the backpropagation error, the number of computation needed is of the same order as the forward computation. In the forward computation, I am calculating f, backward computation calculating f prime. So, it is not particularly different. So, the backpropagation of error, the number of computations needed are of the same order as the forward computation, right. Now, one backpropagation, one pass of backpropagation gives me all the partial derivatives with respect to all the weights, right, which means we need the computation time of the order of MW to obtain all the partial derivatives. We know forward pass is of the order of MW, backward pass and forward pass are about the same computation, and one backward pass gives me all the partial derivatives. So, to get all the partial derivatives with respect to all the weights, all the MW weights, I need computation only of the order of MW. Right? This is a remarkable efficiency. I am calculating MW partial derivatives. If I am calculating MW partial derivatives, I can't do anything less than order MW computation. Obviously, I am calculating MW numbers. So, my order of computation should be of the order of MW. That it grows only linearly as MW is really nice. Right. To appreciate this, let us say we want to compute the partial derivatives numerically. Of course, you do the partial derivative computation with us for a particular input. So, if I do analytical expressions, then I will get a huge expression as big as the entire input output mapping of the network for each weight. So, that may not be as nice, but suppose you want to compute partial derivatives numerically. What does that mean? For each weight, I have to perturb the weight and calculate the output, right. I need the derivative of the output with respect to the weight. So, I put the current value of the weight, calculate the output, that I have already done. Now, I perturb one weight, only one weight, keeping everything else same as earlier, and now find the output, and then change in output by change in weight will give me the partial derivative with respect to weight. Right. Now, if I do this, what it means is, because each weight has to be perturbed once, I have to calculate the output of the network as many times as there are weights, which means I need to calculate the output of the network MW times. Each computation of the output will be of the order of MW multiplications. To find all the partial derivatives, I need MW square computations, right, order MW square, because if I want to do it numerically like this, for each weight I have to calculate one output. Calculation of output takes order MW computations. So, there are MW weights, so I take MW square computations. Even if I am using my equations, it will be the same, because for each weight the amount of computation in the equation would be of the same order as calculating the output of the entire network starting from the input. So, if I am doing blindly or in a simple minded manner finding all the partial derivatives, either by brute force crunching of the expressions or through numerical estimation, I would do order MW square computation, whereas backpropagation allows me to do it in order MW. Of course, the reason is in backpropagation we use a lot of interesting properties of the partial derivatives. For example, we show that the partial derivative this can be written in terms of the partial derivatives, that is how the error at a node came, multiplied by the output of the previous node, and because this is known, I only need to calculate these partial derivatives to know these partial derivatives. See, these are weights, partial derivative with respect to, so there are as many partial derivatives here as weights, here there are as many partial derivatives as nodes, right. So, this will certainly save me even if I am doing numerical. We can do the same idea in partial derivatives numerically also. What it means? Instead of finding this partial derivative numerically, I will only find this partial derivative numerically. What does that mean? Instead of perturbing one Wij at a time, we perturb one Njl at a time. So, how many Njls are there? As many as there are nodes. There are ML nodes. So, for each node I have to perturb once. So, which for me each node I have to do one forward pass of computing the output of the network. So, how many times do I compute output now? Earlier I am computing MW times the output of the network. I need how to do it for MW times, I need to do it only ML times. Right. So, my order of computation by perturbing a node at a time is sometimes called node perturbation method of numerically evaluating the partial derivatives. So, which means we only need to calculate order ML forward passes, right, because there are only ML nodes. For each node I want to find the output once, because I found output with NGL already. I perturb only that particular net input, keeping all others constant, and find the output, so that I can get partial with respect to that net input. So, ultimately I need to calculate the output of the network ML times. So, I need to order ML forward passes. Each forward pass has order MW computations. So, I need order ML MW computation. given earlier that MW is ML square kind of thing, ML MW would be like MW log MW, ML will be of the order of log MW. So, we need MW log MW computations if we do node perturbation, but backpropagation is very efficient because it takes only order MW computation to calculate all the MW partial derivative. I can't do any better than this. Right. So, this is one of the reasons why backpropagation is a very popular algorithm for doing gradient descent minimization of the squared error empirical risk on for learning weights in a neural network. Okay. So, let us go a little further to ask how these networks are. Now, let us consider 3-layer network again. Let us say there are m input nodes, let us say the p nodes in the hidden layer and one node in the output layer. As we say, layer 1 is always input layer, layer 3 is always layer L, the last layer is always output layer, everything in between are hidden layers in node, because I have a 3-layer network, there is only one hidden layer. So, let us suppose there are p nodes in the hidden layer, m nodes in the input layer and one node in the output layer. So, such a network will represent a function from Rm to R. So, let us write an explicit expression for this function. What will be the function? This output is this weight into this output plus this weight into this output, this weight into this output, all added up and passed through the activation function of this, right. So, I can write that as f of summation j is equal to 1 to p as many as hidden nodes w j 1 2. This is the weight that connects node j in layer 1, node j in layer 2 to node 1 in layer 3 into f into output of node j in layer 2. What is the output of node j in layer 2? If I want any node output, I have to find weighted sum of all the inputs. Inputs are the outputs of these layers is x's. So, I make the corresponding input multiply by the weight and pass it to a activation function that gives me the output here. So, it will be that. Now, let us suppose this network uses the activation function. This is the activation function for the output node. Let us say we use linear activation function. So, the output node is linear. Now, this weight only depends on the index in the hidden layer, right. So, that 1 and 2 are constant. So, let me write it as beta j, j goes from 1 to p. Then I do not need this 1 here, w's are only here. So, I can write a w j x I. Plus here I did not put the bias, I told you earlier each node can have bias. So, let us put a bias. So, if I have a one hidden layer network with p nodes in the hidden layer, mind you, whenever I am representing a function, the number of nodes in the input and output layers are fixed based on the dimension of the domain and range of the function, right. So, if I am running a function from Rm to R, there should be m input nodes, one output node, that is fixed. So, the only thing I do not know is if I am using one hidden layer, I do not know how many hidden nodes I can have. Let us say they are p, then this is a general expression for a function represented by a neural network with one hidden layer with p hidden nodes. Beta j's represent the weights between the hidden node j and the output node, there is only one output node. Wij represent the weight between the ith input node and jth hidden node. X's are the inputs and beta j is the biases for the hidden nodes. I am not putting the bias for the output node. So, this is the form of the function represented by this 3-layer network. Now, we can ask the question, what kind of functions can be represented like this? I am asking if I consider functions from Rm to R, some functions can be written like this, some function may not be written like this, depending on what f I am choosing. Right. So, I am asking for what all functions, will there be some beta j's, wij's and bj's, so that they can be written like this, right. That will tell me what kind of functions my network can represent. So, the question is what kind of functions can be represented like this. We now state a theorem says that if p is sufficient, then this 3-layer network can approximately represent any continuous function over compact sets in Rm, right. Given any compact set in Rm, if those of you do not know what a compact set is, simply take it as a closed, is like a cylindrical set of closed intervals. Okay. So, think of it as a closed bounded set in Rm. Okay. So, given any compact set Rm, we can approximate any continuous function by such a network. Okay. I will formally state the theorem now. So, for simplicity notation for compact set, you can simply think of it as some closed interval to the power m, that is what we are going to do. So, here is the theorem. Let phi be some bounded strictly monotonically increasing continuous function. This will serve the purpose of our activation function. So, given some function phi which is bounded strictly monotonically increasing and continuous, which is all what our sigmoids and our tan hyperbolic everything satisfies. Let script C of I m be the set of all continuous real valued functions on I m, where I m is the cylindrical set in is the set of all is the 0 1 to the power m. I m is the unit hypercube in m dimensions. Right? The interval 0 1 raised to the power m is the Cartesian product of the interval 0 1 m times. So, 0 1 to the power m is the is the hypercube of side 1 in R m, okay. One of its corner is at the origin, right. If you call that as I m, this is a simple compact set to take an R m. C of I m is the continuous real valued function that map I m to R, right. So, any continuous function, continuous real valued function that maps elements of I m to R is in C I m. We are taking I m because, as I said, we only want to consider any compact set in R m, and this is as good as any other compact set in R m. Okay. So, let C I m be the set of all continuous real valued functions, and we are asking, can I represent every function in C I m using a network, and we can. Then, given any function in C M, given any continuous function, continuous real valued function h and any epsilon, I want h represented with an epsilon accuracy, then there exists a p, some number of hidden nodes, and real numbers beta j, b j, w I j, that means the weights, so that if I calculate a function h hat, which is actually what this 3-layer network represents, with p as the number of hidden nodes and this beta, b and w I j are the corresponding weights. If I calculate h hat like this, then the maximum difference between h and h hat, maximum taken over all points in I m, is less than epsilon. That means, given any epsilon and given any function h, I can always find a 3-layer network with some number of hidden nodes and some weights, such that the output of the network does not differ from the actual value of the function by more than epsilon for any input. So, this is a very remarkable theorem. This tells me that my 3-layer network is good enough to represent any continuous function to an arbitrary accuracy. Right? Of course, I do not know what 3-layer network I want, but what do you mean by what 3-layer network? The only thing that is not known in a 3-layer network is p, how many hidden nodes I should have. This theorem only tells me that a p exists, I do not know what the value of p is. So, what the theorem says is that a feed forward network with a single hidden layer, but with sufficiently many nodes in that hidden layer, can approximate any continuous function to an epsilon accuracy for any epsilon. Right? So, essentially, if I put sufficient nodes in my hidden layer, I can represent any continuous function. So, this is a very good parametric class of functions, because I do not need I can represent all continuous functions, and that is good enough for me. Okay. Now, see, in this representation I am using phi as the activation function of the hidden nodes, that is why we chose phi to be bounded, strictly monotone, increasing, continuous, and so on. Okay. Okay. The only catch is, of course, that I do not know how to estimate this p. So, given some samples, nobody will tell me how I can choose a particular 3-layer network. A particular 3-layer network, by a particular 3-layer network, we mean how many hidden nodes in the hidden layer should I choose. But such as it is, if I choose sufficient number of hidden nodes, then the theorem guarantees that I can find a representation. Now, because the supremum difference between h x and h hat x is bounded. Essentially, I can find the corresponding weights for a given p by minimizing the squared error. So, if I can actually find the global minimizer of the squared error, then I can arbitrarily I can get a good approximation to any continuous function, right. So, in this sense the algorithm that we have given is reasonable. This theorem gives me some justification for the algorithm. Essentially, even if I use only one hidden layer, if I put sufficient nodes in the hidden layer, and if my algorithm can get me the weights that are global minimizers of the squared error loss, then I can approximate any continuous function. So, the theorem assures that the feedforward networks are good models for generic parameterized class or nonlinear functions and provides some justification for the algorithm we have presented. Of course, our algorithm is gradient descent and hence it gets stuck in local minima. But if I can go to global minima, I get weights, and if I start with sufficient number of hidden nodes, I can represent. So, essentially we set out to have a good parameters class of nonlinear functions, and the models we considered are good parameters class of nonlinear functions. The theorem assures us that, and we can certainly find the weights by minimizing the empirical list under squared error loss. Okay. Let us look at it a little more carefully. So, this is what a three-layer network represents: j is equal to 1 to p beta j f of I is equal to 1 to m w I j x I plus b j. When we did our linear least squares regression, we said that any function in the linear regression model can be written as j is equal to 1 to p beta j phi j x, right. So, if I think of all this part, f of summation I is equal to 1 to m w I j x I plus b j, this is something that depends only on j, because summed over all the I. Of course, it depends also on the x's. So, I call it phi j x. So, this structure is same as this structure, right. We already know how to learn this using our linear regression models. What is the difference, right? We said that the linear regression models, linear least squares can do this, right. So, what is extra that this is giving? The difference is, in the linear least squares, these phi j's have to be fixed beforehand. They are not, they can't be chosen based on the data. Whereas here the phi j's are this, the phi j's involve this w I j and b j, and w I j and b j are learned using the data. So, the phi j functions are not prefixed, they are learned using the data. Right? In the linear regression model, these phi j functions are prefixed, like x, x square, x cube, so on. Right? Whereas here I am choosing the wij's and beta j's are learned from the data. So, it is effectively as if I am learning the phi j's needed using the data, right. So, the difference is that the basis functions are not fixed beforehand. The basis functions themselves are adopted or learned using the training data, right. These phi j's actually come from here, they contain adaptable or adjustable parameters. So, when I am not using fixed base function, if you remember again and again when we talked about linear regression, we kept on saying as long as the basis functions are fixed. So, that is the issue. If the basis functions themselves are adopted, then I can learn nonlinear functions. Okay. So, you can think of the output of the hidden layer. So, now if I go back to my 3-layer network, if I just consider the hidden to output layer, this is like that beta j phi j x, because the outputs of this is phi j x, right. Once the weights are all fixed, right, the phi j's are fixed. So, this is like a fixed basis representation. So, we can think of what we are doing using backpropagation is learning these weights, so that instead of representing input as x 1 to x m, we are representing as phi 1 x, phi 2 x, phi p x. The phi 1 x, phi 2 x, phi p x is a good representation, because now a linear model can represent the function you want. So, the entire issue of learning these weights is like transform this representation x 1 to x m representation to phi 1 x, phi 2 x, phi p x representation, right. So, we can think of backpropagation as learning a proper internal representation. It is not nothing to do with only one hidden layer, there can be any number of hidden layers here. So, essentially from the input up to the last but one layer is a representation of the output. So, backpropagation allows you to learn the right representation, so that now under that representation a simple linear model can learn, right. That is what my backpropagation is doing. So, I can think of the output of the hidden layer as a proper representation input, so that now we can use a linear model for predicting the target. So, this is the reason why backpropagation algorithm learns proper internal representation, that is how it is termed. Okay. So, one often says that use backpropagation to learn proper internal representations. There is one more issue you should consider. We said that the 3-layer network can approximate any continuous function. It is very nice. So, it is a very good model for nonlinear functions. That is the reason we are studying it, and so on and so forth. But then there are many other ways of representing all continuous functions, right. This result is also true for many representations. For example, I can use polynomials, I can use Fourier functions. There are many families of basis functions to represent all continuous functions. Continuous functions are complex sets, it forms a vector space. So, there will be some basis for it, and in terms of basis I can represent anything. What does that mean? Given any continuous function h, we can always represent h x equal to I is equal to 1 to infinity, because this function space may have infinite dimensional, beta I phi I x, where phi 1 phi 2 so on is a basis for that vector space. So, such a representation always exists, and polynomials is one particular thing, as we already know. For example, in R to R, every function can be represented given the basis 1 x, x square, x cube, so on, right. All continuous functions or complex sets can be represented as polynomials. So, there are many such basis functions phi I, and I can represent any continuous function as an infinite sequence, infinite summation basis function like that. Once I know that this infinite sequence converges to h x, there will always exist a number m such that the sum will be equal to epsilon, equal to h x would be within epsilon of h x. So, I can always have a p such that if I take the sum up to p, then that h hat x is a good approximation to h x. So, what is the big deal again? We have the 3-layer network also represents all continuous functions, this also represents all continuous functions. In this case, I am using fixed basis, in 3-layer network I am not using fixed basis. What is the difference? By using neural network, we are adopting the basis function rather than choose a fixed basis. Is there some advantage? Yes, one can show that the neural network, whose weights globally minimize the sum of squared error, would achieve better approximation accuracy than the function learned using fixed. So, given a fixed number of examples, a neural network will give me better accuracy than any of the fixed basis functions. Essentially, that is what is meant by I can achieve better approximation. So, even though I can use fixed basis and still get the result that any continuous function can be represented, by using a neural network I can get better approximation. That is, for the same number of examples I get better approximation. So, this is what the neural networks where the basis function themselves are adopted are giving me as an advantage. They are universal approximators of continuous functions, and I can learn it with better accuracy than using a fixed basis. Okay. So, there we stop for today. Next class we will look at a few more issues of backpropagation. Thank you.